Example 5 says, use the graphics below to help you find the volume of the solid obtained by rotating the region bounded by y equals x squared minus 1, y equals 2, y equals 8, and x equals 0 about the y-axis. Now this one's nice because basically our graphs are done for us. We have this shaded region here, and we're taking that and rotating it about the y-axis, which this indicates the rotation about the y-axis. And then we have this nice little drawing for us here, and the thickness of this blue slice of bread is delta y, and then I need the radius of my slice of bread, and our function is y equals x squared minus 1, but because our slices of bread are being stacked on top of each other vertically, that means we're going to need to integrate with respect to y. So notice that here our lowest slice of bread would start at y equals 2, and our top slice of bread would end at y equals 8. And so we need to have an expression for the radius in terms of y. So what I can do is I know that we have our curve y equals x squared minus 1. I can solve this for x because our radius is really just the x value, because we're measuring the distance from the y-axis to a point on our curve, and that's the x value there. So I'm going to go ahead and solve my equation for x by adding 1 to both sides. We get x squared is equal to y plus 1, and then if I take the square root of both sides, I get x is equal to the square root of y plus 1, and we could put plus or minus, but we want the positive value there. And so now let's go ahead and set up our integral. We have the volume is equal to, our limits of integration are 2 to 8, and these slices of bread are circular cylinders, or discs rather. So we have pi times the radius. We just said that the radius was the square root of y plus 1, and we need to square that and then multiply by the height, which in this case is delta y, or dy, when we change it into a definite integral. So I can factor out pi outside of my integral, and then I'm going to square that expression to get y plus 1, and we have dy. Now I can take the antiderivative, so we have y squared over 2 plus y. I forgot the pi here. And then we're evaluating this from y equals 2 to y equals 8. So that is equal to pi times 64 over 2 plus 8. And then minus 4 over 2, which is 2, plus 2. And that is going to simplify to be 36 pi. Example 6 says, determine the volume of the solid obtained by rotating the portion of the region bounded by y equals the cubed root of x and y equals x over 4 that lies in the first quadrant about the y-axis. So unfortunately in this situation we have to do our own graphing, and we're not given those nice graphs. So the cubed root of x, it looks something like that. That's a very rough sketch. And then x over 4, that's a linear equation. It has a slope of 1/4. And notice that we are limited to the first quadrant. And so really, I should just draw in my first quadrant the cubed root function. So maybe it looks something like that. And then I have my linear function, y equals x over 4, and I'm just going to graph, and maybe they intersect somewhere there. So I'll just stop there, and that's what we have in the first quadrant. And get rid of some of that. All right, and here's our y-axis, here's our x-axis, and it wants us to rotate about the y-axis. So I'm gonna put my little spinny rotation indicator there. And the way that I'm going to draw this is I'm going to kind of reflect this over the y-axis. So it almost looks like it's going to make, you have to envision this in your mind for the three-dimensional shape. It almost looks like it's going to make a bowl that's hollow in the middle. And the thing about this one is because it's hollow in the middle, if I were to chop it and make a cross section, what's going to happen is our cross section is a washer. And if you recall from earlier, a washer is essentially a circle that has a hole in the middle. So it's almost like a donut. And I'm just going to choose some arbitrary place to draw my washer to indicate this is what my cross section looks like. So that's a washer, and I'm going to add some thickness to it so it kind of looks like a donut. And the thickness of this is delta y. And because our washers or our donuts, however you want to think about it, because they're being stacked on top of each other vertically, our integral is going to be with respect to y. So if I'm trying to think of my limits of integration, I need to think about where my lowest donut or my lowest washer starts and where the highest one ends. So the highest one is kind of like over here. And so what I need to do is I need to figure out where my two curves are intersecting, because I need to figure out where this ordered pair is. So we have the equations for our two curves. I'm going to go ahead and make it so that both of the equations that we have are solved for the x variable. So I'm going to take this equation, I'm going to cube both sides, and that's going to give us x equals y cubed. And then this equation here, if I solve that for x, I end up getting x is equal to 4y. Now that they're both equal to x, I can set these two equations equal to each other. And if I do that, I get y cubed is equal to 4y. So now let's solve this equation for y so that we can figure out where these two curves intersect. I'm going to subtract 4y on both sides and then factor out y. I can now use the zero product principle, and I can set y equal to 0 and y squared minus 4 equals 0. I already kind of see visually that they intersect at the origin, so I can visually see that. And then here, I can add 4 to both sides, and if I take the square root of both sides, I get y equals plus or minus the square root of 2. So it turns out that they also intersect in the quadrant 3, but we're only concerned with quadrant 1, so I don't really care about the negative value. That means that this ordered pair here has some x value, and then the y value is 2, and really at this point it's not all that important to figure out what the x value is, since we're integrating with respect to y. So I'm going to redraw my washer here. And the thing about the washer is that essentially we are looking at two different radii, and maybe I'll draw it out here so that we can kind of see this better. I have my little donut here, and if I want the area of this donut, which is going to be this shaded part here, if I want that area, I need to find the area of the larger circle and subtract off the area of the smaller circle so that I can cut out that little donut hole essentially. And the way that we do that is here is the center of both of these circles, because these are concentric circles. So I have the distance from here to here, and then I also have the distance from here to here, and the larger of those radii I'm calling the outer radius, and then the smaller one I'm calling the inner radius. And so if you recall from earlier, the area of this donut, if you're thinking about it in 2 dimensions, the area of the washer is equal to pi times the outer radius squared minus the inner radius squared. And again, I just want to emphasize that this is not a standard notation. I'm just abbreviating outer radius and inner radius. And if I want the volume, if I'm thinking about it as a 3-dimensional donut, then I would think about what the height or the thickness is, and in this case we're calling it delta y. So it's going to be pi times the outer radius squared minus the inner radius squared, and then times the height, or in this case the thickness. So let's go ahead and set up our definite integral now. Our lower limit of integration is going to be 0. Our upper limit of integration is going to be 2. And then we have pi. And now we need to actually figure out what our outer radius is and our inner radius. And they are essentially affected by our 2 curves. And so the linear curve, again, is the curve x equals 4y. And then the other one is x equals y cubed. And if you look, the outer radius is the one that's touching the linear curve. So our outer radius is going to be 4y. So here I'm going to put 4y quantity squared minus my inner radius is the distance from the y-axis to when we touch the other curve. And so that's the x value, which is y cubed in that case, when it's touching that inner curve. So that's going to be y cubed squared. And then again, we are integrating with respect to y because we're stacking our donuts on top of each other vertically. So this gives us, I'm going to factor out pi, and then the quantity 4y squared is going to give me 16y squared, and then minus y to the 6th power dy. That's going to equal pi times 16y cubed over 3 minus y to the 7th over 7. And we're evaluating this from y equals 0 to y equals 2. And if you evaluate this, you will end up getting your final answer being the volume is equal to 512 pi divided by 21. So there is our final answer. Example 7 says, set up the integral that would find the volume of the solid generated by revolving the region bounded by y equals x squared minus 2x and y equals x about the line y equals 4. Okay, so I went ahead and I did a quick sketch of the 2 curves that were given. So my lower curve here is y equals x squared minus 2x. And then my line here is the line y equals x. And this is the first example that we've seen where we're rotating about a line that is not either the x-axis or the y-axis, and we're rotating about the line y equals 4. So let's just say 4 is right here, and I'm going to draw this dashed thing here, and now I'm going to take my graph and I'm going to kind of reflect it. So it looks something like that. That was my poor attempt at a reflection. And then I'm I want to draw my cross section now. So what's going to happen is, and this is supposed to be symmetric, so pretend that it's symmetric. And I have this cross section here, and I know the thickness of it will be delta x. And I have a washer or a donut, so I'm going to have essentially my inner radius which will be the distance from the line y equals 4 to where I touch my curve here, and then the outer radius will be the distance from the line y equals 4 to my curve down here. So this blue thing will represent my outer radius, and then the shorter one, the shorter line segment that I drew, will represent the inner radius. I forgot to draw my little rotation symbol. Now what I want to do is I'm going to calculate some distances, and the distance from here to here, so I'm essentially measuring the distance of the distance from the line y equals 4 to the x-axis, and that's not changing, so that distance is 4. And then because of the way that I drew my picture, I now also want to calculate that distance, and I would want to add them together so that I have my outer radius. And this distance here is y equals, because it's the y value, and it's y equals x squared minus 2x. Now, in the way that I've drawn the picture, in this particular instance, the y value is negative, so what's happening is I'm really subtracting off 4 minus that quantity, and we can see that as well even if I draw a cross-section where I am taking the distance from there to here, so that would also represent an outer radius. And so in that instance, what I'd be doing is I'd be doing 4 minus the y value, because now the y value would be there. So it'd be doing 4 minus that to calculate that distance. So let's come over here, and I'm going to again abbreviate OR to represent the outer radius. And the outer radius is changing, and it's given by the expression 4 minus, and then I'm subtracting off this quantity here, x squared minus 2x. Okay, so that was all for the outer radius. Now let's calculate the inner radius. And the inner radius is a similar idea, and I'm going to do some erasing. Now, I know that the distance from here to here is 4, and my inner radius is the distance from here to here, and I know that the distance from here to here is the y value for the linear curve. So my inner radius, if I call this my inner radius, the one way that I could think about it is when I add the inner radius plus y, it gives me 4. So the inner radius plus y gives me 4. And so if I solved that for the inner radius, then that would be 4 minus y. And this is particularly the y that's associated with this line here, y equals x. So if I have my formula for the inner radius, it's going to be 4 minus, and then instead of y, because we're going to end up being integrating with respect to x, I'm going to replace it with x, because again, y equals x for that line. And now, if I take a cross-section and I want to calculate the cross-sectional area, we've been calling it a of x. So in this case, a of x is equal to pi times the outer radius squared minus the inner radius squared. And so that's going to equal pi times our outer radius. Maybe I will distribute this negative sign here. So we get 4 minus x squared plus 2x quantity squared minus 4 minus x quantity squared there, because that was our inner radius. Okay, so now let's go on to talking about the volume of this three-dimensional shape. My left boundary is, or this ordered pair is the origin, so that's going to be 0, 0. And I still haven't found what that value or that ordered pair is, and I need to do that because I need to come up with my limits of integration. So let's go ahead and do that. I have my two curves and I want to set them equal to each other, so I get x squared minus 2x is equal to x. If I subtract both sides by x, I get x squared minus 3x is equal to 0. Then I can factor out an x. And so we end up getting that the two curves intersect at x equals 0 and x equals 3. So my volume now is the definite integral from 0 to 3 of pi times essentially this thing here. And this question is only asking us to set up the integral. It's not actually asking us to solve it. But if I were to simplify the highlighted expression, that's going to end up simplifying to x to the 4th minus 4x cubed minus 5x squared plus 24x dx. So we could just stop here. It asks us to set up the integral. It doesn't actually ask us to find the volume. So we could just stop here, but in case you are curious, if you solve that definite integral, the volume ends up being 153 pi over 5. And that concludes this example.